Hello there, and welcome back to Science for Sleep. Tonight we are going to explore something that should not exist, something that breaks the rules of the universe so completely, so absolutely, that even the scientists who study them spend their careers in a state of quiet disbelief. They are places where space ends, where time stops, where the laws of physics, the same laws that govern every atom in your body and every star in the sky, simply cease to apply. And yet they are everywhere, scattered across the universe in numbers that dwarf imagination, lurking at the center of almost every galaxy ever observed, including the one you are living in right now. Tonight, where are you listening from? Is it late where you are? Is the room quiet? Is the world outside your window still? Because tonight we are going to travel somewhere that makes even the largest things you have ever imagined feel small. We are going to explore black holes, one of the most astonishing, most terrifying, and most strangely beautiful phenomena in the known universe. So settle in. Let your body grow heavy. Let your breathing slow. And let's begin. The universe has a stage. That stage is called spacetime. Space and time are not separate things. They are woven together into a single fabric, and that fabric is not rigid. It bends, it curves, it stretches. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This is the elegant foundation of Einstein's general relativity, and it is the key to understanding everything that follows tonight. When matter is dense enough, the curvature of spacetime becomes extreme. When it becomes extreme enough, a threshold is crossed. And on the other side of that threshold is a black hole. A black hole is not a hole in the ordinary sense. It is not empty. It is the opposite of empty. It is a region of space where so much mass has been compressed into so small a volume that gravity becomes so strong that nothing, not matter, not energy, not even light, can escape. The first person to mathematically predict the existence of black holes was not Albert Einstein, although it was his equations that made them inevitable. It was Karl Schwarzschild, a German physicist who solved Einstein's field equations in 1916 while serving on the Russian front during World War I. He sent his solution to Einstein from the trenches. Einstein was astonished. Schwarzschild died just months later. He never knew what he had found. Most black holes begin with a death. When a star that is at least 20 to 30 times more massive than our Sun reaches the end of its life, its core collapses. For billions of years, nuclear fusion in the core had generated outward pressure strong enough to resist the inward pull of gravity. When the fuel runs out, the pressure disappears. Gravity wins. The core implodes at nearly a quarter of the speed of light. The outer layers rebound in a cataclysmic explosion called a supernova. And at the center of all that violence, a black hole is born. The boundary of a black hole, the point of no return, is called the event horizon. It is not a physical surface. There is nothing there to touch or see. It is simply the threshold beyond which escape becomes mathematically impossible. The escape velocity, the speed you would need to break free from gravity's grip, reaches the speed of light. And since nothing travels faster than light, nothing leaves. If you compress the Sun, all 2 octillion tons of it, down to a sphere with a radius of about 3 kilometers, it would become a black hole. The Sun itself would disappear. A region of absolute darkness would take its place, a region from which no light could ever escape. A black hole with 10 times the mass of our Sun would be barely 60 kilometers across, less than the distance across a city. Yet the gravity at its edge would be strong enough to trap light itself. The smallest known black hole is called J1650. It has a mass of 3.8 times our Sun, and its diameter is approximately the length of the island of Manhattan. A city-sized object with the gravity of 4 suns. The black hole at the center of our galaxy, called Sagittarius A star, contains 4.3 million times the mass of our Sun. If it were placed at the center of our solar system, it would extend only to about 1/5 of Mercury's orbit. Extraordinarily small for its mass. Extraordinarily dense. The black hole at the center of the galaxy, Messier 87, the first black hole ever directly photographed, contains 5.4 billion solar masses. The image captured in 2019 by the Event Horizon Telescope showed not the black hole itself, which by definition cannot be seen, but the glowing ring of superheated material orbiting just outside its edge. Light from behind the black hole bent completely around it by gravity, creating a ring of impossible fire. Among the largest known black holes is TON 618, a quasar in the constellation Canes Venatici. It contains 66 billion times the mass of our Sun. If placed at the center of our solar system, it would swallow every planet out past Neptune and keep going. You could fit nearly 40 of our solar systems inside it. Then there is Phoenix A. With an estimated mass of 100 billion solar masses, it may be the most massive black hole ever discovered. 100 billion suns, compressed, silent, waiting. And these are only the ones we know about. Scientists estimate there are up to 40 quintillion black holes in the observable universe. 40 quintillion. That is a 40 followed by 18 zeros. The space directly around a black hole is one of the strangest environments in the known universe. Matter falling toward a black hole does not fall straight in. Like water draining from a bath, it spirals. It forms a disk. This accretion disk, as it is called, is one of the brightest structures in the universe. As material spirals inward, friction and collision between particles heat it to temperatures exceeding 1 billion degrees. The disk glows. It blazes. It outshines entire galaxies. Near the event horizon, light itself can orbit. Just outside the boundary, at a region called the photon sphere, the gravitational pull is so precisely balanced against the momentum of light that photons circle the black hole endlessly. If you were to hover at the photon sphere and look straight ahead, you would see the back of your own head. Your own light, having traveled completely around the black hole and returned to your eyes. Gravity does not just bend space, it bends time. The closer you are to a massive object, the slower time passes. This is not a metaphor. It is not a philosophical statement. It is a measurable, observed, confirmed property of the universe. Clocks on satellites in orbit tick faster than clocks on Earth and must be adjusted to keep GPS systems accurate. The difference is tiny near Earth. Near a black hole, it becomes extreme. If you were to hover just outside the event horizon of a massive black hole and someone watched you from far away through a telescope, they would see your movements slow. They would see your watch tick more slowly. They would see you redden, your light stretched to longer wavelengths by the intense gravity, and eventually they would see you appear to freeze, hanging motionless at the edge of the horizon, the last light you emitted slowly fading, stretched into invisibility. They would never see you cross the threshold. From their perspective, you would be frozen at the boundary of the black hole forever. From your perspective, nothing unusual would happen as you crossed the event horizon of a very large black hole. There is no wall there, no sign, no sensation. You would simply be inside, and the universe outside would shrink to a single bright point behind you. If you fell into a small black hole, the experience would be very different and very brief. Because your feet would be closer to the singularity than your head, they would feel a stronger gravitational pull. This tidal force, the difference in gravity across your body, would be extreme. It would stretch you, pull your feet toward the center faster than your head, compress you sideways, elongate you in the vertical direction. Scientists call this spaghettification, and while the name is almost charming, the process is not. Your body would be pulled apart into a long, thin stream of hot plasma, stretched thinner and thinner until individual atoms were separated, and then the particles within atoms, and then perhaps even the fundamental constituents of matter itself. Everything that was once you ripped apart and drawn toward the center. If you fell into a supermassive black hole, the tidal forces at the event horizon would be gentle enough that you might not feel them at all. You could cross the point of no return in complete comfort, without any sensation of having done so. Only the mathematics would know. Only the equations would mark the moment. And by then, there would be no turning back. Inside the event horizon, something extraordinary happens to the relationship between space and time. Outside a black hole, space extends in all directions and time flows forward. Inside the event horizon, the singularity at the center lies not just in a particular direction in space, it lies in the future. In every direction you might travel inside the event horizon, you are moving toward the singularity. You cannot turn away from it any more than you can turn away from tomorrow. Trying to escape the singularity inside a black hole is like trying to escape tomorrow. Tomorrow is in your future. There is no direction you can go to avoid it. The singularity itself is where general relativity breaks down entirely. It is the point where the equations produce infinities, infinite density, infinite curvature, a divide by zero in the mathematics of the universe. Most physicists believe that the singularity as described by general relativity is not a true description of what actually exists at the center of a black hole, but rather a signal that general relativity is incomplete, that a deeper theory, one that unifies gravity with quantum mechanics, would describe what is actually there. We do not yet have that theory. What we do know is that every black hole, regardless of what fell into it or how it formed, can be completely described by just three numbers: its mass, its spin, its electric charge. Everything else is lost. The information about what made it, whether it was stars or gas or planets or ancient light, is apparently gone, erased. This is what physicists call the no-hair theorem. A black hole has no distinguishing features beyond those three numbers. Every black hole of the same mass, spin, and charge is identical, the way fundamental particles are identical. In this sense, black holes are among the simplest objects in the universe. Almost all black holes spin. They are born from dying stars, and dying stars spin. As the core collapses, angular momentum is conserved, and the rotation accelerates enormously, the way a spinning ice skater accelerates when they pull in their arms. Some black holes are estimated to rotate at speeds approaching 90% of the speed of light. A spinning black hole does something to space-time that a stationary one does not. It drags space itself around with it, the way a spinning ball drags the air around it, but on a cosmic scale. This effect, called frame dragging, creates a region outside the event horizon called the ergosphere. Inside the ergosphere, space-time is being dragged around so powerfully that nothing can remain stationary. Not rockets, not light, nothing. Everything inside the ergosphere must rotate with the black hole, whether it wants to or not. The tide of space-time is irresistible. The ergosphere offers, theoretically, the possibility of extracting energy from a rotating black hole. If a particle falls into the ergosphere and splits in two, one piece falling inward and one piece escaping outward, the escaping piece can carry away more energy than the original particle brought in, drawing the energy from the rotation of the black hole itself. This is called the Penrose process. In principle, a civilization of unimaginable technological advancement could harvest energy from a rotating black hole indefinitely. In 1974, Stephen Hawking made one of the most surprising and important discoveries in the history of theoretical physics. He showed, using the mathematics of quantum mechanics applied to the curved spacetime near a black hole, that black holes are not entirely black. They emit radiation. Slowly, imperceptibly, but they emit it. The mechanism involves the quantum nature of empty space. The vacuum, the apparent emptiness of space, is not truly empty. Quantum field theory tells us that the vacuum constantly fluctuates, with pairs of virtual particles spontaneously appearing and annihilating in fleeting bursts of existence. Normally, these pairs, a particle and its antiparticle, appear together and annihilate together almost instantly, borrowing energy from the vacuum and returning it so quickly that nothing observable results. Near the event horizon of a black hole, something different can happen. One particle of the pair can fall inside the horizon before the annihilation occurs. The other escapes. To an observer far away, it looks as though the black hole has emitted a particle. The energy for this particle comes from the black hole itself. The black hole loses mass. This is Hawking radiation, and it has a profound implication. Black holes, given enough time, evaporate. How much time? For a black hole with the mass of our Sun, the lifetime before complete evaporation is approximately 10 to the power of 67 years. That is a 1 followed by 67 zeros. For comparison, the current age of the universe is roughly 13.8 billion years. The Sun would need to wait for an amount of time so much longer than the current age of the universe that no human analogy can adequately capture it. Imagine an hourglass filled with 1 grain of sand for every particle in the observable universe. Every 10 billion years, a single grain of sand falls. By the time the hourglass is empty, a solar mass black hole would not have lost even a fraction of a percent of its mass. Supermassive black holes have even longer lifetimes. For TON 618, with 66 billion solar masses, the lifetime stretches toward 10 to the power of 100 years. A googol, a 1 followed by 100 zeros. A number so vast that it exceeds the number of particles in the observable universe. In 2021, researchers using data from the LIGO and Virgo gravitational wave observatories confirmed one of Hawking's fundamental theorems about black holes. The area theorem, which states that the total area of all event horizons in the universe can never decrease, was verified through observation of 2 black holes merging. After the merger, the surface area of the combined black hole was larger than the sum of the 2 original black holes. Hawking was right. And yet, the most profound puzzle about black holes remains unsolved. The information paradox. Quantum mechanics contains a fundamental principle called unitarity, which essentially states that information is never destroyed. If you know the complete quantum state of a system at any moment in time, you can, in principle, reconstruct its entire past and predict its entire future. Information is conserved. This principle underlies all of quantum mechanics and has never been observed to be violated. But black holes appear to violate it. When matter falls into a black hole, the information it carries seems to disappear behind the event horizon. And when the black hole eventually evaporates through Hawking radiation, Hawking's original calculation suggested that the radiation was purely thermal, carrying no information about what had fallen in, which would mean the information was permanently destroyed, which would mean quantum mechanics is wrong. This is the information paradox, and it has occupied the minds of the greatest physicists in the world for nearly 50 years. In 2019, a series of papers proposed a potential resolution. Using techniques from string theory, researchers found evidence that the Hawking radiation might not be entirely information-free. That subtle quantum effects, including something resembling virtual wormholes connecting the interior of the black hole to the exterior, might allow information to escape after all. Imprinted on the radiation in an extraordinarily subtle and scrambled form, but not destroyed. The picture that emerges from this work is extraordinary. It suggests that the interior of a black hole and its exterior may be the same place, connected by quantum geometry. that space and time themselves might be emergent properties arising from underlying patterns of quantum entanglement, that the universe might, in some deep sense, be a network of quantum information, and that black holes, which appear to consume and destroy, may actually be the universe's most extreme information processing systems. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, the black hole at the center of our own galaxy. For the first time, humans had seen the silhouette of the object at the heart of the Milky Way. We had photographed the darkness at the center of our home. Scientists at MIT and other institutions have recently proposed that certain ancient black holes, called primordial black holes, may have formed in the very early universe, in the first fractions of a second after the Big Bang. If such black holes exist and are small enough, they may now be in the final stages of their evaporation. A 2025 study proposed that the most energetic neutrinos ever detected might be signatures of these final evaporations. The last gasps of black holes born at the dawn of time, evaporating now, 14 billion years later, just as Hawking predicted. Every galaxy we can observe has a supermassive black hole at its center. These black holes did not form from the collapse of a single star. They grew. They consumed gas and stars and smaller black holes over billions of years. The exact origin of the supermassive black holes at galactic centers remains one of the open questions of modern astrophysics. When two black holes merge, the event is among the most violent in the universe. The two objects spiral toward each other over millions of years, their mutual gravity radiating energy as gravitational waves, ripples in the fabric of spacetime, propagating outward at the speed of light. In the last fraction of a second of the merger, more energy is released in gravitational waves than all the light emitted by all the stars in the observable universe combined. LIGO detected the first gravitational wave signal from merging black holes in September 2015. The signal lasted less than a second. It was the sound of two black holes becoming one, a billion light years away, 500 million years before complex life appeared on Earth. Black holes do not only consume, they also create. The enormous gravitational fields around active black holes launch jets of material, plasma moving at close to the speed of light, extending from millions of light years from the galactic center. These jets carry energy and matter into the surrounding cosmos. They regulate the formation of stars in their host galaxies across cosmic distances. The black holes at the centers of galaxies are not passive consumers. They are engines that have shaped the large-scale structure of the universe. Every star that has ever formed in the Milky Way was shaped, in part, by the black hole at its center. And every atom in your body was forged in the heart of a star, which means every atom in your body was shaped across billions of years of cosmic history by the existence of a black hole. You are, in a very real sense, the distant product of the most extreme objects in the universe. That was 100 facts about black holes. And now the universe contracts back to the quiet room around you. The concepts that filled the last hour, event horizons and singularities, spaghettification and Hawking radiation, the information paradox and the quantum nature of space-time, they are not leaving. They will settle into the background of your mind tonight, the way everything eventually settles. And somewhere, unimaginably far from where you lie right now, a black hole is doing what black holes always do, curving space-time around itself, bending light, slowing time, waiting with the patience of something that will outlast the stars themselves. It does not know you are thinking about it tonight, but in some strange and beautiful way, you are made of the same universe it belongs to, the same fabric, the same laws, the same darkness and light. Let your breathing slow. Let the weight of it settle. Science for Sleep will be here when you return.